Hi, my name is Nir Bar-Gill. I've been here at the Hebrew University as a joint appointment between applied physics and physics for 10 years now, since 2013. And my research is focused on quantum information, simulation, and sensing experimentally using the platform of atomic defects in solid structures. Specifically, our work has been focused on NV centers in diamond, but we've recently expanded also to other material systems and to other defects, including, for example, boron vacancies in HBN and some other interesting 2D materials. Our work is trying to combine both fundamental aspects of quantum science, quantum technology, and advancing fundamental questions into quantum thermodynamics, control of open quantum systems, going from simple, well understood and well controlled few or single quantum system platforms, all the way up to ensembles of interacting quantum spins, where we have interesting questions associated with many-body dynamics, control, and non-classical states. In terms of applications, we're looking at how we can use these systems and the control that we have over them to create interesting sensors and to apply such sensors for questions in other fields. For example, we've been using these NV centers in diamond as magnetic sensors for studying magnetic van der Waals materials, recently identified, and a lot of interesting open questions are still being studied in this context. And going all the way from these interesting condensed matter systems to questions in chemistry, trying to characterize radicals in small volumes, and even to biological samples and trying to see how we can use our systems to characterize and to learn new things about medical constraints. This is the lab, and as you can see, it's essentially an optics lab. So we're building optical microscopes that allow us to look into these defects in the solid material. These defects are optically active, and that allows us to both address them locally and study their quantum properties, but then also to build interesting optics-based sensors that we can use them for. So what you're seeing here are wide field optical microscopes that we build around our diamond NV center platform that allow us to read out the optical signature of these NVs, and it carries with it the magnetic information which we want to measure, for example, for our condensed matter experiments, where we're looking at the magnetic properties of van der Waals ferromagnets and other types of materials which we can look at in these newly built systems. One kind of side project that comes out of this, which is actually a project that we're running now in collaboration with ELTA, the radar company, is to try to build a high sensitivity, high frequency sensor that could be relevant for such radar applications that they're interested in. Interestingly, this type of setup, while mainly designed for that high sensitivity application, is actually also well suited for studying highly dense spin ensembles for which interesting many-body quantum effects can appear, and that's also something that we're realizing in this setup. I'll just briefly mention that in addition to these, we also have regular confocal microscopes in our lab. We also have 2 cryogenic confocal microscopes that we use for measuring at low temperatures, both for applications and for fundamental quantum questions. And we're also building a super resolution STED-based microscope that would allow us to measure beyond the diffraction limit and look at interesting dynamics associated with magnetic materials, excitations, magnons, fermions, and so on.